Okay. Good morning. Let's get started. Firstly, I haven't had a chance to look at your midterms as yet. I was at a conference last week, so I will look at it over this weekend and I'll pass it to you next week. Okay. Hope you had a good break. Did you get a break or no? Good. Um, okay. So let's see. This is week 8, and we will have classes till week 13. The exam is on week 14 on Monday. Okay, I planned it for Monday. I will tell you the exact timings. So, what we'll do in the second half of this class is we will continue with LPs. So, this week I will discuss network flows. Okay, and I'll talk about network optimization. Next week, I'll spend a bit of time talking about a couple of other algorithms for LP, specifically the ellipsoid and the interior point methods. And then we will segue into integer programming and basically spend about 4 weeks doing like discrete optimization and ideas in that. Okay. So, uh, so the class. So for this week, the content is our content is going to be network flows and network optimization. Okay. We will discuss this. It's a very useful class of problems that show up in many areas from engineering. People doing electrical engineering, mechanical, to things like people studying social networks, okay, communication networks, traffic flows. So many applications that shows up. And again, you can take a full class or even a full PhD level course just on network flows and network optimization. And there are full books on this topic. Okay. So what my goal for this course will be is to think about some canonical or important network flow problems, see how LPs are the right ways to think about formulating them, and we will sort of take the simplex method and think about what it means for network optimization. Okay. And we can also do more specialized problems, more specialized algorithms. I won't do specialized algorithms for these problems in this course. It's not the right venue, but I can point you to references which you can look at your own time. Okay. 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 So before we get started, are there any other questions, queries from? Are there any concerns on your mind? Any questions? Anything? Okay. All set to go? Okay. Okay, cool. Okay, so let's start then. Okay. So what are network flow problems? Okay. So essentially network flow problems, okay, so the word flow already means that something is flowing. Okay. So network flow problems essentially are LPs, okay, uh, um, that arise on graphs. Okay. And of course, the key thing will be that we need to understand what we are talking about, what is the flow, what type of flow problems can show up. Okay. So I'm going to spend a bit of time discussing just the basic graph terminology. I mean, you might have done some graph theory in your undergraduate or your master's if you've done it. If not, it's fine. Most of what we will require is sort of fairly basic, but I do want to ensure that basic graph terminology is clear first. Okay. So we're going to just spend a bit of time talking about what graphs mean for us, what we require for this course, and how the LPs will then show up later. Okay. So there are two types of graphs. There are going to be essentially there are two types. There's an undirected graph, okay, and there are directed graphs. Okay. Okay. So undirected graphs and directed graphs. Okay. So what's a graph? So a graph is nothing but a combination of vertices and edges. Okay. So V is the vertices, also nodes. Okay. And E are edges or arcs. Okay. Okay. Now for an undirected graph, okay. Now throughout this, we will only look at finite graphs. So which means that think about the number of vertices or nodes being finite and number of edges being finite. Okay. That is a theory for graph theory and infinite graphs. It's not going to be important for us. Okay. So everything here is infinite. So all graphs are of finite size. So all graphs that are of interest to us are finite graphs, finite size graphs. Okay. So what do I mean by finite size graphs? Essentially, finite number of vertices and a finite number of edges. Okay. So there's nothing which goes off to infinity. Okay. Okay. Now, what is the difference between an undirected and directed graph? So in terms of notation, for undirected graphs, okay, so these are all graphs. Okay. Okay. For undirected graphs, essentially our edges will be of the type. So an edge will be of the type I, comma j, and I'm going to use curly brackets here to represent undirected graphs. So what does this mean? Essentially, it means that if you take node I and node j, two different nodes, there is an edge E indexed by I and j, which connects I and j. Okay. So we'll think about what these nodes might mean, but maybe these are two people who know each other, they're friends. So that's an edge. Okay. So if I'm a friend of somebody, we form an edge. If I don't know somebody, we don't have an edge on the graph. Okay. If we have a directed graph, okay, so this is for undirected graphs. If we have directed graph, the edge would be of the type I comma j. Okay, so there's a notion of direction here. So what does direction mean? In when I have I comma j, essentially it's an edge which goes from node I into node j. Okay, so the notion of direction here is important. So for example, what this might mean is like flow or let's say current. Current can flow from I to j, but it cannot flow from j to I. Or person I can influence person j. Okay, so maybe there is, I don't know, a famous personality. You follow their trends. That person can influence your tastes. They buy a brand, you buy a brand. But maybe if you buy a brand, they are not influenced. So there's a notion of direction. Okay. Okay. So clearly in this notion, ij is not the same as ji. Okay. These are two different graphs. Two different edges. So ji would be an edge which goes from j to I. Okay. But for us, in undirected graphs, of course, I can write ij or ji. It doesn't matter because there's no notion of direction here. Okay. Now you can also always clearly convert an undirected graph. You can take the edge of an undirected graph and think of it as a directed edge by essentially replicating the edge in two directions, right? So you can take, so you could take an undirected edge. I could take this I comma j, and I could have in principle created an edge, directed edge from I to j and j to I. So I just double the number of edges and so this is essentially equivalent to this directed edge, right? So yeah, flow can happen either in this direction or this direction, which captures the notion of undirected edges. Okay. So you can transform undirected graphs to directed graphs, okay, by this just simple, just doubling the number of edges. Okay. Okay. Now, a couple of other things that we will be using is, so throughout, we will assume that, I assume throughout that, that there are no self loops, okay? No self loops. What does a self loop mean? It means an edge which goes from I and comes back to I, okay? So a self loop is not going to be allowed in any of this. It's not going to be relevant for the class of problems we are going to think about. We are thinking about flow. Okay. So we're never going to have things like this. Okay. This will never be allowed. Okay. But you can have in some other applications, you can have self loops. Okay. But it won't be something that will show up for us. And the other thing that we will not have is, and no multiple edges between pairs of nodes. I will show you later, even if you have it, we can model it, no multiple edges between the same pair of nodes. Okay. So what this means is, if I take node I and node j, and there's a link connecting I to j, there's exactly one link. I won't have multiple links going between these. If there are multiple links, there are ways to transform it. But in terms of just the theory that we will look at, we will just consider one link between a node. I mean, there could be there's exactly one link going from I to J or J to I, or maybe there are two, both of them, but I won't have many of these things. Okay. At least for the theory, we will later on when we write down when we think about network simplex and the ideas for that, we will require this. Okay. Okay. Any questions with this so far? Like just the basic terms. So where might undirected or directed graphs show up? So for example, you think about directed graphs. I mean, the most natural thing one would think about is like, like road networks. You have most road networks. You have vehicles which can drive in one direction. Okay, so you have a road. Flow happens in one direction. Okay. Um, Another example could be something like let's say something like Twitter, like a social network like this. Like I mentioned, some you follow somebody, they post, you get their post, you post, they don't see your post basically. Okay. So there's a notion of directions. So undirected graphs might be things like just friendship networks, like friendship networks. So in most cases, friendship is by I'm a friend, you're my friend. Okay, so there's no notion of direction. Or maybe things like interaction, like protein interactions and so on. So it depends on the how two proteins interact with each other. If they interact with each other, is there a link and so on? So this is in biology, and you can find many such examples. And you probably have done this in your own, some other applications you've studied on your own. Okay, so I'm not going to write down all the examples here, but just a few examples. Okay, any questions so far with these? Okay. Okay, so next we'll just go to some basic terms that we require, just terminology, okay, that you will require. Okay, so I'm going to start with just thinking about these things for undirected graph, and maybe I'll just draw a graph as we just work through this. So I'll just use an example as we go through, as I define these terms. Okay, okay. So a few terms that we require. Okay, so first is the degree of the node. Okay, so what's the degree of a node? Sorry, degree of a node. So degree of a node I. So remember, an undirected graph is G equal to V and edge. Okay, vertices and edges. Okay, list of all vertices, list of all edges. So actually, let's first write down the vertices and edge set just to be sure we are clear on this. So what is the vertex set here? It's 1, 2, 3, 4, 5, 6. There are 6 vertices in this graph. What is the edge set? So this is a vertex set. What is the edge set? 1, comma 2, 1, comma 3, 2, comma 3, 2, comma 4, 3, comma 4, 4, 5, and 4, 6. Okay. So there are 6 edges, sorry, 6 vertices, 7 edges. Okay. Okay. So what's the degree of a node I? Essentially, it's just the number of edges incident to node I. Okay. Incident to node I. So for example, the degree of, let's say, node 1 is clearly 2. I've got 2 nodes that is connected to, or 2 edges which are going out of this. Okay. So the highest degree node in this graph is node 4. Node 4 has a degree 4 in this example. Okay. Okay. So what's the neighborhood of an edge, a node? Neighborhood of a node, essentially the nodes that are connected to it. Okay, nodes connected, or nodes may be adjacent. Let's maybe say adjacent to I. Okay. So, for example, in this graph, the neighborhood of node 1 will be nodes 2 and 3. Okay. So the neighborhood of 1 of 1 is basically 2 and 3. Okay. Okay, so all these are fairly straightforward. Okay, so we have degree, we have node, we have neighborhood. Okay. The next thing we require is the notion of paths, cycles, okay, and walks. Okay. So what's a walk? A walk in a graph is just a set of nodes that you're traversing, okay, using the edges of the graph. Okay. So a walk is just a finite sequence of, so a walk is basically a finite sequence of nodes. Let's call this I1, I2, all the way up to IT, okay, where every edge, IT, let's say IT plus 1, is an edge in the graph. Okay. So it's basically, as I, so I'm traversing from one node to another node using the edges of the graph, and I've got a finite sequence of such nodes. Okay. So for example, a walk in this graph might be to start from, so here's a walk. Let's say you start from 1, you go to 2, maybe then you go to 4, maybe then you go to 3, 1, 2, 4, 3. Maybe then you go back to 1, then maybe you walk to 2. Okay, 1, 2, 4, 3, 1, 2. That's a walk. I'm only using edges of the graph, and clearly it's a finite sequence of nodes that I'm traversing. Okay, so that's a walk. Okay, so what's a path? A path is when there's no repetition. So you cannot come back to the same node. Okay, so a path is a walk with no repeated nodes. Okay, so this is not a path because I've gone from 1, I've moved to 2, I've then moved to 4, then I've come back to 3. Okay, so 1, 2, 4, 3 is a path. Okay, so path. So for example, 1, 2, 4, 3 is a path. But at some point, I'm repeating a node. So that's no longer a path. Okay, so this is a path. 1, 2, 4, 3. Another path is, for example, 2, 3, 4, 6. Okay, what's a cycle? A cycle is when the start and the end node of a walk are the same. Okay, so a cycle is a walk where walk with I1, IT minus 1 distinct, and the last node IT is equal to I1. So you start, so you have distinct nodes, and the last node that you get to is the same as the first node. So for example, this walk contains a path, contains a cycle. The cycle is clearly 1, 2, 4, 3, 1. So you repeat the node, so you have completed a cycle. Okay. 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 So all these are fairly straightforward. Any questions for this? Any of the terms here clear? Okay. Two other definitions we require. The notion of connected graphs and complete graphs. So what's a connected graph? A connected graph is for every distinct pair of nodes, for every distinct pair of nodes, there exists a path connecting the two nodes. There exists a path connecting the two nodes. Okay. So let's look at this graph and check if it's connected. Okay. So I can go from 1 to 2. I can go from 1 to 3 directly. I can't go from 1 to 4 directly, but I can go 1 to 4 or 1, 3, 4. Okay. I can go from 1 to 5. I can go from 1 to 6. And you can check in this graph that from any one node to any other node, I can find a path to get there. Okay, there is no part. For example, for 5 to 6, though don't have a direct link, I can clearly go 5, 4, 6. Okay, so this is an example of a connected graph. Okay, so this is a connected graph. So a graph, for example, which may not be connected is something like this. That's a disconnected graph. I cannot go from node 1 to node 3. This is disconnected, right? Okay. Okay. The next one I require is complete graphs. So what's a complete graph? It simply says that for every distinct pair, there's actually a link or there's an edge connecting the two pairs of nodes. So for every distinct pair of nodes, that exists a edge connecting the two nodes. Connecting the two nodes. Okay. So let's look at the example. So clearly 1 and 2 are, I mean, there's a direct link. 1 and 3 has a direct link. 1 and 4 does not have a direct link. Okay. So this graph is not a complete graph. Okay. So this is connected, but this is not complete. Okay. So a complete graph will have roughly basically, if n is the number of nodes, order n squared edges. Okay. I mean, you can count it precisely. It'll be what n minus 1. It will be n 1 plus 2 up to n minus 1. You add it up. Okay. But basically, roughly order n squared. So a complete graph, for example, of size 3, or let's say size 4, would look like this: 1, 2, 3, 4. There should be an edge between every pair of nodes. That's a complete graph. Okay. I think this is all the terms we require for now for an undirected graph. As and when if I require more terms, I'll tell you. Okay. Okay. So anything here which is unclear terminology wise. So as I start using some of these terms, it should be comfortable for you. Okay. All these definitions can be specialized to directed graphs. Okay. So we just spoke here about undirected graphs. Okay. So there's a natural, so the only thing in directed graphs is what? There's a sense of direction. Okay. So there are two ways you can define things on directed graphs. So let's say I give you a directed graph of this type. Let's take this example. Okay. I can define things like directed. So one way is I can use all the definitions for the undirected graph by just forgetting the directions, right? So I could have just taken the underlying undirected graph, which is defining the connection here. Okay. And I could use all these definitions from before. Okay. With respect to this undirected graph. Okay. So this is the undirected version of this graph. Okay. But clearly with directed graphs, I can define all these things using directions. So for example, I can define for a node the in degree and the out degree. Okay. What is the in degree? The number of nodes, number of edges coming into a node. Okay. So in degree is number of edges incoming to, so in degree of node I incoming to I. Okay. So, and similarly, out degree will simply be number of edges going out of node I. Out degree is the number of edges outgoing from I. Okay. So for example, let's take node, maybe let's take node 3. So node 3, the in degree of node 3, in degree of node 3 is what? What's the in degree of node 3? How many edges are incoming to node 3? 1, right? What's the out degree? 2. Okay. Of course, if I take the corresponding graph and I just ask you what is the degree of this node, simply if you take the undirected graph, the degree is 3. So you can now use the definitions on the underlying undirected graph or be precise with the directed notions, right? So you can define everything out degree is Two, so similarly, you can define an in neighborhood, out neighborhood. You can define a directed path, a directed walk, a directed cycle. So, for example, a directed path on this graph is what? One, so a directed path. So, one, two, three, let's say 1, 2, 3, 4 is a directed path. Okay. If I take 4, 3, 1, that's not a directed path, but it's a path on the underlying undirected graph. Okay. So if you have the notion of directions, you have to be careful with it. Similarly, you have directed cycles. So 1, 2, 3, 1 is a directed cycle in this graph. Okay. So after this, everything, all definitions, it should be very clear with just the, just intuitively you can see it from the graph. Okay. Okay. So I won't be defining everything, but you should be able to understand all these definitions now for directed graphs. Okay. Any questions with this so far, these terms? Okay. So this is fairly basic at this point. So there's a special type of graph that's going to be relevant for us because this graph is going to show up. It's obviously an important graph, but also it's going to show up later on when we think about the network flow problem. Okay. So a special type of graph, so trees. So a special type of graph, and there are many special types of graphs, by the way. Okay. But I will look at one special type which is going to be relevant for us, which is what is called trees. Okay. So this is a very, very important class of graphs. Essentially, it gives you graphs that are connected and have the fewest number of edges. Okay. Okay. So let's define this. So what's a tree? So a tree is an undirected graph that is connected. So what does it mean to be connected? I can go from one node to any other node. I can find a path that is connected, but it is sort of sparse. It doesn't have too many edges. Okay. And has no cycles. Okay. So somehow there's a notion of being connected. So there are enough edges to go from one node to another node, or enough ways to get, or that is a way to get from one node to another node, but there are not too many ways. Okay. That's a fact of having no cycles. Okay. So here's an example. So let's take some examples of trees. So for example, this is a tree. In fact, it's called a star tree. Okay. Just looking at the shape of this, there's basically one node which has a high degree and every other node is connected into it. So it's like this, what is called this hub and spoke. So there's a center node which links to many people or many other nodes. Okay. So here's another tree. This is a path graph. There's a single path. Observe that from any node, I can get to any other node. Okay. That's a tree. Okay. Of course, you can have other types of trees. It need not only be of this type. Sorry. So you can have all types of trees. Each of this is a tree. Okay. Okay. Any questions with that definition? There are no cycles here. Okay. Okay. So the nodes of, so by the way, nodes of degree 1 in a tree, nodes of degree 1 uh, are called basically leaves of the tree. Okay. So all these are the leaves of the tree. That's a leaf. That's a leaf. So all these three nodes are leaves. These two nodes are leaves, and so on. Okay. Okay. Uh, what's a spanning tree? Okay. So a spanning tree is a so a spanning tree of a graph is a subset of the graph, okay, when I say subset, meaning you take a subset of the edges, subset of the graph that forms a tree and spans, or basically connects all the nodes of the graph. Okay. Okay. So let's say, so again, let's take an example. So let's say I've got an underlying graph. Okay. So let's say my underlying graph is like this. This may not be a tree. Okay. But let's say there's a graph like this. Let's say that's my graph. Okay. This is my graph. A spanning tree on this graph is what? It's basically a subset that forms a tree. A subset of this that connects all the nodes and forms a tree. So, for example, this is a spanning tree. 1, 2, 3, 4. That's one spanning tree. There are many other spanning trees. So, can you tell me one more spanning tree in this graph? Just give me another one. One? One. 1, 2, 4, 3. Okay. 1, 2, 4, 3. That's a spanning tree. Okay. So these are, so basically what? You have a network, you're trying to find a subset of this network so that all the nodes are connected. So you can find ways to go from one node to any other node. Okay. And it's basically a tree. Okay. So there are no cycles in this. Okay. Now, again, the trees and spanning trees will be important because we are going to use this later in network simplex. Okay. So few properties which we are not going to prove here, but I'll just mention this. And after this, we can go to the precise formulation. So few properties of trees which are important to know. There are many properties, but which are relevant. Again, these are extremely important graph structures. Okay. Because they are, I mean, in some ways, they keep the graph connected and they are sparse. They're not, you're not having too many edges there are no cycles. So you don't have like multiple ways. So it's sort of the bare bone network in the graph. Okay. Okay. So some properties of trees which sort of are intuitive, but I just want to mention this is one. So for any distinct pair of nodes, there is an unique path to connecting the nodes. Okay. Connecting the two nodes. Okay. So this is one property. Okay. So remember, the graph is connected, a tree is connected. So that means I can go from one node to any other node. But there might be multiple ways to do this in general. Okay. In a tree, because there are no cycles, I will always have a distinct or a unique way to get from one point to any other point. So if you take any, let's say node 1 and node 5, I have precisely one way to get from node 1 to node 5. Okay. Because there are no cycles. So there's no way to enter a node. If you have cycles, you can enter a node and exit the node. Okay. But because you don't have cycles, there will always be a unique path between every pair of nodes in the tree. Okay. Next property, if we add an edge, to a tree, it forms it forms an unique cycle. Okay. So let's take a tree. Let's say I decide to add an edge. Okay. Some edge. Let's take, I add the edge 3, 4. It forms a unique cycle. Okay. If I take 5, 7, it forms a unique cycle 4, 5, 7. Okay. Because the edge to which you're connecting the two nodes, they become basically, there's a way to exit and enter those nodes. So essentially you can, so it's quite intuitive to see. Again, you can formalize this, but I won't do it here. I thought it was 7, right? Okay. So hopefully it's clear. Okay. So the moment I add an edge, I'll form one cycle in this graph somewhere. Okay. Is that clear? Okay, good. 3. Okay, so every tree with one node, okay, so if a tree has, if there's only one node, there's no arc basically. So every tree with more than one node has at least one leaf node. So what's a leaf node? Degree 1. Okay. So if you have a tree with, so there should be at least one node, which is a leaf node. Okay, in this tree, there could be more than one, but it's always at least one leaf node in a tree. Okay. So in this graph, the leaf nodes are 3, 5, 6, and 7. Okay. And maybe the last one, which is relevant for us, is a spanning tree on a graph of n nodes has n minus 1 edges. Okay. If you have n nodes with n edges, somewhere there'll be a cycle. Okay. So if you have n nodes, so let's say I've got 2 edges. The moment I put a third edge somewhere, I'm going to create a cycle. Okay. So any spanning tree on n node graph will have n minus 1 edges. Okay. And yeah, I think these properties, are they sort of clear? Yeah. Yes. This is not a tree. Sorry. To a tree, that's no longer a tree. So this, once I add an edge to a tree, it's no longer a tree. I'm saying the new graph that is formed. This new graph is not a tree now. The new graph is not a tree. You can't add. I mean, if you have a spanning tree, let's say, and you add an edge, it's no longer going to be a tree. It's going to become, there's going to be a cycle somewhere. Okay. But I mean, you can have things which are disconnected. So, I mean, but of course, a tree, essentially a spanning tree spans all the nodes of the graph. So if the underlying spanning tree has to connect up all the nodes basically. Okay. And actually, there's a notion of a forest. Maybe I'll just say this is not going to be relevant for us, but just for so what's a forest? Actually, a forest is a disjoint union of trees. A forest is a disjoint union of trees. Okay. So basically, what a forest is so if you have a graph like this, this is a graph on 9 nodes. These are not 3 different graphs. I've numbered them from 1 to 9. Each of them is a tree, and there's a disjoint union of trees. Okay. So if there are many trees and they're disjoint, so this is clearly a tree. This is not a tree, right? The entire thing, it's not connected, right? Okay. Are the terms clear? Any questions on the terms? Okay. So this was just terminology, just to ensure that we all are familiar with these terms. So now I can actually define a basic network flow problem. Okay. So I will define what a network flow problem is. We will take what is called the minimum cost flow problem, and then we will take special cases of this problem. And today I'll mainly spend time on formulations. I'll probably talk about the simplex method next time, probably. We'll see how it goes. Okay. So what's a network? Okay. So we have only graphs so far. So far we have a graph. Essentially, a graph is a structure about connections between whatever these nodes might mean. Okay. So when you say network, okay, Essentially, it's a graph. Okay. And we are going to, so throughout, I'm going to focus on problems on undirected graphs. I'm sorry, on directed graphs. Okay. Undirected graph problems, we can convert it to directed graphs by simply having these two edges, right? So I'm going to just focus on directed graphs for this for our discussion. Okay. So network is a directed graph. Okay. With additional numerical information on edges and or nodes, depending on what type of information you have. Okay. So for example, what is the type of information? Okay. So the information that we are going to be focusing on, essentially, they're going to be uh, uh, types of information we'll look at. Okay. So what is the information? So one, BI is going to be the supply. Actually, I'm going to put the word external here just to make this clear. External supply slash demand at node I. Okay. So every node might have a number BI, which is given data, which tells me what is either the supply or the demand at the node. Okay. And we're going to use a particular, I'm going to use a particular convention here. So if BI is positive, I'm going to think of it as a supply node. If BI is negative, it's going to be a demand node. Okay. And if BI is zero, it's going to be what is called a transshipment node. Okay. So think about, let's say, flow of products on a network, okay, or flow of some flow. Okay. So at any node, I'll give an example soon, but at any node, let's say I'm pumping in 5 units of flow into that node. Okay. That means the supply there will be 5. Okay. Maybe at some other node, I'm pumping out 2 units out of the system network. So demand there is 2. Okay. So this graph we'll see has to be balanced for the optimization problem to be well set up. But that's basically the definition. Not definition, that's the interpretation of BI. Is that clear? We'll make it precise with numbers later on. But is it clear what I'm saying here? Okay. Okay. The second type of information we'll look at is bounds. So maybe there are bounds on links. So lower and upper bounds on flow on the edge I comma j. Okay. I'm talking about directed graphs here. So I'm using this brackets. So that means that on a particular link or a particular edge, I can send between LIJ and UIJ units of flow. I mean, think about a road network on a particular road. At any point in time, you might be able to send, I don't know, 20 cars or 30 cars. You can't send 150 cars on the road at any point in time, right? So there's some capacity which these networks have, or you cannot send too much flow depending on how much it can take. Okay. The third type of information that we will look at is cost, because we are optimizers, or there's an optimization class. We're trying to optimize some object on this network. So there's going to be a cost Cij, which is going to be cost of unit flow along edge ij. Okay. So if I use a particular link and I send 1 unit of flow, I pay a cost of Cij. If I send 10 units of flow, I pay 10 times Cij. So the more I send on this edge, I'm paying a cost. And because we are going to be focused here on linear cost functions, because we're doing this is a linear optimization class, so it'll be Cij times Xij if Xij is flow on the arc. Okay. Okay, so is it clear? These three, I mean, they're very straightforward. This is exactly like what we did for LPs. So now I'm going to set up the minimum cost network flow problem. Okay, so here is a very important class, and the class that we'll be focusing, the class of problems, minimum cost network flow problem. Okay, maybe I'll just abbreviate this also, minimum cost network flow, or MCF. No, okay. So I'm going to write down an LP. Okay. So what are we trying to figure? So we are given a graph, right? We have a graph. We are trying to figure out on this graph how to send flow. Okay. So that we are minimizing costs. So my decision variable will be Xij, which is going to be the flow on edge Ij, which is my decision variable. Okay. So all my variables in this problem are going to be on the edges of the graph. Okay. So what's my optimization problem? I want to minimize total flow. So I take every edge in this graph. I pay a cost Cij times Xij on this. Depending on my flow, if I send no flow, I get zero cost. If I if I send a particular amount of flow, I send a linear function of that. Okay. So remember, I'm sending flow. Okay. I'm deciding the flows on this network. So imagine I'm a company, I'm going to ship items out. I decide how much to send on every link of this graph. So this is what I control. Okay. This flow cannot be arbitrary. It has to satisfy two constraints. The first constraint is what is called flow conservation. Okay. So let me write it down. So I'll first write down the formulation and then I'll show you a figure just to illustrate this. Xij for every j such that ij is an edge in the graph minus summation xji for every j such that j comma I is an edge in the graph equal to bi for every I in my vertex. Okay. So what is this constraint telling me? Okay. So I'm going to just show you, I'm just going to write this down with a, actually, let me first write down the two constraints and then we can discuss it. And then the second is capacity constraints, which is saying that Xij has to be between the lower bound and the upper bound for every edge in the graph. Okay. So that's my minimum cost network flow problem. Okay. So let's first think about what the flow conservation is telling me. So this is flow conservation at node I. Okay. So let's think about node I. What happens at node I? I've got a supply. This is Bi. Okay. So Bi is positive means it's supply. Okay. That means the flow is incoming. Okay. If Bi is negative, in my notation, so if there's a negative flow coming in, it means that there's positive flow going out. Okay. Okay. So, but essentially, Bi is capturing supply. Okay. Okay. Fine. Now I've got edges which come into this node, and I've got edges which go out of this node. Okay. What is flow conservation going to tell me? If I take all the flow, so what is this? These are all the flows. This is incoming flow. So take all the flows xji for every j such that j comma I is in E. So this is all my incoming flow, inflow. Inflow plus my external supply. This flow is coming from other nodes in the graph. Okay, so I've got some in neighborhood of this graph. So this is what is coming because of the network from previous nodes are sending me flow. This plus my external supply has to be equal to my outflow, which is summation xij for every j where ij is in E. This is, I'm taking all the nodes to which I is connected. Okay. So another way of saying this is, if you take the difference between the outflow and the inflow, that should be equal to the external supply. External supply coming in has to be balanced by the difference between the outflow and the inflow. Okay. This is the most basic law that we have to satisfy. Is basically conservation. You think of conservation of energy, conservation of momentum, conservation of flow. This is the basic law that any physical flow has to satisfy. Okay. Okay. And the other constraint is straightforward. It simply says that on a particular link, ij, I cannot send more than what the capacity is. So if I've got a lower bound and an upper bound on a particular link, xij cannot exceed, has to lie within this range. That's by my link capacity constraints. Okay. This problem is an LP, right? It's linear in my objective. It's linear in my decision variables, linear equality constraints, linear inequality constraints. It's an LP, but it is a special type of LP because the constraints of this LP are determined by the network structure or the graph and by the flow conservation constraints and capacity constraints. So these are LPs which are specialized for this class of problems. Now, because of the structure of the graph, because of the fact that there's a graph structure underlying the problem, not every LP has a graph structure underlying it. But because there's an underlying graph which structure which the LP is modeling, it turns out that these LPs can be solved even more efficiently. And specifically, these LPs can model many interesting class of flow problems. Okay. So what we'll do is next I will tell you about special cases of this problem. We'll look at a couple of cases which are the most relevant. Okay. Okay. So any questions with this formulation or the LP formulation? Is that clear? Yes, of course.
In the network, you have the waves equivalent H's.
Yes.
But now we are introducing the cost function. What is the name of this new type of network in which you have the cost and also the waves?
So it depends on what the okay. So when you say weight,
The
huh?
is of the XIJ
Yes.
waves, right?
Xij is not a weight. Xij is the flow. Okay. Xij is not the weight on my edge. On an edge, okay. So just to be clear on this, so on the edge, okay, there is a cost Cij, and there is a capacity Lij and Uij. Okay. This is the telling you the flow on this edge can be between Lij and Uij. Cij is the cost for unit flow on this link. So if I send 5 units of flow, firstly, this 5 units has to lie between these two upper and lower bounds. Otherwise, I cannot send 5 units of flow. Second, if I send 5 units of flow, the cost I'm going to pay for this is 5 times Cij. So if you've got some other, I mean, it might be the case that you've got some additional information, like maybe you've got some other information on this, some other weights or something, and there are other constraints. I mean, this is a basic problem. Of course, you might bring in other constraints which are possible. Then it will, the structure of the LP will get changed a bit. Okay. If you have other, I mean, you might have other constraints. Actually, we'll see next that certain types of constraints can be easily incorporated using this formulation itself. I will tell you that in a bit. But basically, there is a cost on every arc. So if you're thinking profit maximization, maybe there's a profit on each arc. You then just maximize the profit. But you're sending, you're trying to use the link as much as possible, or in this case, minimize the costs. Is that answering your question? Okay.
It's okay.
No, but are you thinking of weights? I mean, I'm just trying to. It depends on what your weight means for your problem. I mean, I don't know what your weight means for your problem. The easiest, yeah. I mean, maybe we'll do a couple of examples. It'll be clearer, and then we can come back to this conversation. Then, yeah, yeah. Okay, it's 10:57. Let's take a break. We'll start in about 5 minutes, and then we'll do a couple of examples of problems you can formulate like this. Okay, let's take a break.
After this final exam, I will go back to China for 3 weeks. And come back here again. I hope it again. But my supervisor said that somebody will start my project. So maybe I start, but but we have a 7
Oh, yeah.
Yes. Yeah, this move. I should go to sleep. This one? Yes. In terms, this I don't want to see anything of this. Would you like to see your score next week? He said he will return next week. Yeah. I think I'm on good. But you finished earlier than others. Yeah. No. I did not finish. I gave up. You give up. No, I was looking through all the questions and I just thinking myself, there's no way I got any time to actually complete the questions. So I was like, so the last minute, man. So the last minute, then you did all the questions. Until the time's up. I've already studied. Prepare my qualifications. I don't think I can get a minus. So you're sitting in the QE exam room right now? This week over. Yeah, my meetings for other classes. Yeah, I have a meeting yesterday night for the machine learning in ISTV class. Last night. Yeah, that's it. And that is a simple and easy exam. Compared to this? Yeah. It's much more easier than this. I wanted to take another module actually. There was no like midterms. It's just projects and assignments. That's it. What was it? The module that I gave was so the module is I'll give you yeah, that's just presentation and the assignment. And then it also I had a presentation, meeting presentation last morning. Oh, you give the readers. Yeah. I'm gonna do that. Because I don't want to do that first. What is it? Like, okay, like this here. Oh, is the game theory class is here? The content is not so easy, but the assignment and the project. Well, this. Yeah, also be confusing with this stress. But it's not. Yeah.
Okay, shall we get started? So I want to now talk about a couple of problems that can be formulated as network flow problems. Okay, min cost network flow problems. So the first one is shortest path, which is one of the most canonical examples of a network optimization problem. The shortest path, and there are many variants of this problem. I'm going to take the most basic one. So what's the shortest path problem? So given a directed graph, okay, with a specific source node. So source node S and a destination or an end node T. Okay. So this is what is called the ST shortest path. So I've got a fixed node, source node S, end node T, arc lengths Cij. Okay. And we're going to assume these are non-negative for every edge in the graph. Find the shortest, find the shortest path from S to T. Okay. Okay. So that's the shortest path problem. So here's an example, just to make this precise. So let's say I've got a network. Okay. Let's say I have a network. Okay. And let's say for now that my source node is 1. So this is my starting node, and my end node is 5. Okay. So let me call this S, and this is 5. So my destination node is 5. Okay. So I want to go from node 1 to node 5 in the shortest possible way. It depends on what my costs on these edges are. Let's say for this problem, let's say the cost of every edge is 1. Okay. So I'm just focusing on a problem where Cij is 1 for every edge in the graph. So essentially, this is a problem where I just want to find the least number of links or least number of edges to get from 1 to 5. Okay. If there is a different cost, which is not just which is just not 1, that's easy to model. Okay. So we can write this as a, so this can be, so, okay. So what are we trying to do? So we're trying to send, so think of this now as a flow problem. What do I want to do? I want to take 1 unit of flow. I want to take 1 unit of, sorry. I want to take 1 unit of flow and send it into node 1. And I want this 1 unit of flow to come out from node 5. Okay. I can formulate this as a minimum cost network flow problem. Okay. where my input, my supply at node 1 is 1, my demand at node 5 is -1. Every other node in this graph, it's what is called a transshipment node, which means that I have no, so if my edges are not, if my nodes are not S or T, I don't, there is no external flow coming into this node. Okay. So this is a balance graph. I've got a network. I'm trying to send in 1 unit of flow. This 1 unit has to come out from some other side, which is I'm forced to be destination 5. Okay. So if I try to do this, there are many paths I could have chosen. I could have gone, for example, 1, 2, 3, 5. That gave me a cost of 3. Okay. So the shortest path in this graph is actually clearly 1, 4, and 4, 5. Okay. So what we could have done is we could have solved this problem. In this problem, I could have set Lij to be 0. Okay. And you can set Uij to be 1, or actually you can set Uij to be infinity. That means you have no upper bounds on this problem for every edge in this graph. And you can solve the minimum cost network flow problem. Okay. You just minimize the sums of the cost times the flow, where you satisfy flow conservation, except there is a supply of 1, a demand of 1 at nodes 1 and 5, and my flow is between 0 and infinity. Okay. The claim is that if you solve a minimum cost network flow problem, you will actually find the shortest path on this graph. Okay. Okay. Now, there is a catch here in the following sense that nowhere in this problem did I say that Xij has to be 0 or 1. Right. So, I mean, what is the optimal solution to this problem? There'll be a flow of 1 on this edge. There'll be a flow of 1 on this edge. So that's flow conservation. That means there should be a flow of 0 on this edge. There should be a flow of 0 on this edge, a flow of 0 on this edge, 0 coming in, 0 going out, 0 on this edge. So I'll have zeros on all these edges, flows, 1 on this, it's balanced. It satisfies my LP constraints, and it will give me a cost of 2. Okay, so the optimal cost, so shortest path is 1, 4, 5 of length 2. But nowhere in the LP I said I'm going to choose these to be binary, right? Because LP just is solving. So somehow, so I'm going to make a note here. We will see later that the optimal solution for this LP will automatically be integral and 0, 1 value. Okay. Which means that by solving just LPs, I'll be able to actually find the shortest path. Okay. Because I mean, in principle, it's quite clear. You either use a link or you don't use a link, basically. Right? Okay. So we'll come back to this because we need some theory for this. Okay. And the decision variable in this problem ultimately will be, you can think about it, Xij will be 1 if Ij is used on the shortest path and 0 otherwise. I'm just solving Xij between 0 and infinity. Automatically, this is going to happen. Okay, so we'll come back to why this will happen later. Okay, so is that clear? But in terms of pure flow problems, it should be quite clear that this is a, you can think of this as a flow problem on this graph. Okay, any questions with this? Yeah. It can, Uij can also be said to be 1. It's fine. If you set Uij too small, then of course you cannot balance it, right? So suppose, so you have to be careful what your upper bound capacity is. You know, if I'm trying to send in 1 unit of flow here, if for some reason I push this float, so all I'm saying is you don't have to say anything to me about the upper bounds on the flow. You can let it be whatever it is. Because I'm trying to minimize cost here in this problem, it will not push Xij to be high because all my costs here are non-negative. Okay. If you were to put, you could have also put Uij to be 1, it will also work. If you put it less than 1, you're going to be in trouble. Okay. But essentially, all I'm saying is you can solve a network flow problem where you just have make this 0 and make this, don't say anything for this. I mean, if I don't put an upper bound, if I upper bound is infinity, it's like saying there's no upper bound, right? So I'll just have essentially this constraints and xij is non-negative. So it's like a standard form LP. Okay. Okay. Any questions? Other questions? Good. Okay. Okay. Now, clearly, shortest path problems, it's the most basic uh, problem that one can think of on networks. The shortest way to route from point A to point B. Every transportation company has to think about this. When you do flows on your internet, you have to think about this. How quickest to get the data from one point to another. It is the most basic form of flow problems. Okay. And of course, these networks can be gigantic. Okay. I mean, that's the other thing. All these problems, the scale can be very big. Okay. Now, there are some problems which may not automatically look like a shortest path problem, but you can reformulate it as a shortest path problem. So I want to take something like that. An example that it's not naturally clear it's a shortest path problem, but with a bit of thinking, you can see it's a shortest path problem. So this is a problem called dynamic lot sizing. Okay. And this is one way you often do research in these types of areas. You have a particular problem that you're interested in. You try to see, can you transform that problem to something for which there's a well developed theory? Because then you can build on the theory. So sometimes it's about transforming problems to the right form and seeing, okay, I can reformulate this as a particular network flow problem. Then I can use all the theory from there to solve my problem, or maybe it's a slight variant of this problem. Okay. But it turns out dynamic lot sizing will be an example of a shortest path problem. So what's this problem? So I'll explain this problem. It's actually an inventory problem, production problem. Okay. So think about you're having a single type of item. Okay. So let's say you're producing a particular item. Okay. So let's say you're producing cars. Okay. So you're producing cars, you're a manufacturing company, you have to make production plan for the next T time periods. Okay. So you need to figure out how much to produce of this item for every time period. There's a demand for every time period. DT is a demand for item in period T. Okay. So to make this production plan, I need to figure out what is what are my, what is the things that I control. So there are two things you can control in this, in the lot sizing problem. So the key is you can satisfy demand in two ways. Satisfy demand by either, so you can satisfy demand, let's say in period T, by either producing or manufacturing in period T. Okay, so you're a manufacturing company, so you can manufacture in this time period. So let's say in January, you can manufacture for January. Okay, so manufacturing in period T. Okay, or carry inventory from earlier time period T minus 1. Okay. So to satisfy demand, the two things I could do, I could produce in this time period, or maybe I'm carrying stock because I produced it earlier in time and I'm carrying this inventory and I can use this inventory to satisfy my demand. Okay. Why might you do this? It might have been that your production costs were cheaper earlier. So you decided, let's plan earlier, let's produce earlier, and I would rather carry my inventory rather than producing in this time period. So the type of data you're looking at here is CT is the production cost, so unit production cost in period T, and HT is the holding cost or the inventory carrying cost unit. So this is a basic inventory problem. Okay, inventory control problem. Unit holding cost from period t minus 1 to t. Okay. So in period t minus 1, if you're carrying forward inventory, clearly if you're manufacturing, you have to set up your machines to manufacture. If you're carrying inventory, you require storage space. So you have to pay for that. So there's a cost to carrying inventory because you have to keep your space in your warehouse to carry your inventory forward. Okay. So there are two types of costs, production or inventory carrying costs. Okay. Uh, and this is, of course, a finite time period model. So it's a discrete model, discrete time period model. Okay. So is the setup clear? Okay. So I can formulate this as a network problem. Okay. The moment there's time, you can think about a time period model. Okay. So I'm going to have, and I'm going to create now a demand, a node also 0. Okay. So at every time period, I've got a demand D1, D2, DT. The T time periods, that's my demand. To satisfy this, so I'm going to think of this as a network flow problem in the following way. I want D1 up to DT, my demands to be satisfied, which means for this network to be balanced, I need to send in so many units of flow over all these time periods. Okay. Okay. So what can I do in period 1? I can produce. So this is my production. Okay. So this basically is production. The cost of this arc is, for example, C1. The cost of this arc is C2 up to CT, or I can carry forward inventory. I can go from this is inventory. The cost of this is H1. This is H2 up to HT minus 1. Okay. So you got every edge here is either a production arc or an inventory carrying arc. Okay. So for example, at point 2, to satisfy demand, I can either produce or carry forward from period 1. How do I get in period 1? By producing more maybe in period 1. Okay. So that's a network flow problem. Okay. So if so one way you can solve this problem is very simple. So there are two types of problems here. So one is, if this is all your data, I have to essentially find shortest paths from node 0 to 1, uh, zero to 2, and so on, to solve this problem. Okay. So for example, when I'm solving this problem, if I want to satisfy demand in time period 1, I can only produce in time period 1. There's no other way. There's nothing else I can do. For time period 2, to satisfy my demand, essentially I could have produced in time period 1 and carried inventory, or produced in time period 2. For time period 3, I could have done something similar, but now I could have actually found the shortest path from node 0 to node 3 using all these edges. Okay. Each time I find a shortest path from a node to this node, that will actually give me the optimal solution to this problem. Okay. Now, if you have also capacity constraints, or things like you cannot carry forward too much inventory, or you cannot carry forward too much, you cannot make too much production, then you can also formulate this as a network flow problem in the following way. So I want to minimize my production cost. I've got inventory carrying cost. So this is so I'm going to have two types of variables. The variable on this link is going to be x1, x2. The variable on this link is I1, my inventory, I2, and so on. So IT is basically a variable which tells me inventory carried from period T to T plus 1. Okay. So what do you have? Essentially, what this says is, for time, you have the this should be, sorry, IT. So I've got CT into XT, add up for every arc, HT into IT, add up from 1 up to T minus 1. Okay. I mean, there's no reason for me to carry inventory after period T, right? There's nothing in this problem that requires me to carry. I'm solving this for this time period, right? Okay. What is my flow balance constraints? At any time period T, either I carry inventory, I have demand, or I carry forward inventory. Okay. So I'm going to have XT, inventory carried from period T minus 1 into period T. Incoming flow should be equal to demand in time period T plus outgoing flow, because I can carry forward inventory IT. This should be true for every time period from 1 up to time T. Okay. Now, of course, at my starting time period, there is no inventory. So I can simply set, so there's no link here. I can simply set I1 to be 0. Okay. I'm just writing this. So I'm just think of I1 to be 0 and I capital T to be 0, just to, because my variables are only from, I'm only interested in the variables I1 to IT minus 1. So for T equal to 1, I0 is not a variable. It doesn't exist in my problem. So I can simply set I0 to be 0 and capital IT to be 0. Okay, just to, I'm just therefore writing these constraints out. And if you have got capacity constraints, so for example, you say you can't produce too much in a time period, and you might have things like, an upper bound on your capacity, or maybe you can't carry forward too much inventory. These are capacity constraints if there are any. Okay. And of course, when you write this problem, you can also write flow conservation for the node 0, which simply says that the total uh, order quantities over all the time periods has to meet my total demand. Okay. We'll see later on actually that this constraint is redundant. You don't have to write it down. But anyway, for now, it's okay. You can write down the flow conservation for every node. Okay. Node 0, what's flow conservation? To meet my total demand, somewhere over all these time periods, I have to produce that much amount of items, because there's no other way. I'm carrying forward no inventory from my previous problem. Okay. So over this entire T time period, I have to produce so much. I have to meet my demand. I can decide when to do it. That's my choice, but I have to produce so much. Okay. So that's a minimum cost network flow problem. Okay. When I don't have these capacity constraints, I could have solved a shortest path problem. Okay. Now, what we'll show is we'll take a variant of this problem and there are also fixed cost constraints. Okay. Okay. So is the setup clear with the formulation? Any questions? Okay. So I'm now going to consider a variant of this problem. So a variant here is with fixed costs. Okay. So that's actually a lot sizing problem. Okay. So what is a fixed cost problem? So right now, if you think about production costs, if I produce in time period inventory, if I produce XT in time period T, currently my cost is, the slope is CT. This is my production cost currently. So now we're going to look at a variant of this problem where there are fixed costs. Okay, so what is a fixed cost problem? If XT is 0, you pay a cost of 0. But if XT is positive, so in the current model, the cost is CT So when XT is 0, it's 0. When XT is 1, it's C1 X1. When XT is 1, it's CT times 1. In the fixed cost version, there is a cost FT plus CTXT. This cost does not depend on the amount you produce. So it is like what is called setup cost or fixed costs. Essentially, the cost to just set up your manufacturing, no, you have to start your machine, you've got to ensure they're working, so on and so forth. Okay. So in these type of inventory problems, production problems, fixed costs are costs that are incurred as soon as you decide to make production. Okay. So this is not a, I mean, this, so how does this cost function look? At the point zero, it's zero. And then it takes off from this point. So this is FT and then it's CT. So there's actually a breakpoint here. Okay. So this is not a linear function actually. In fact, it's discontinuous. At this point zero, this function is not continuous because this is FT plus CT. At the point zero, my cost is zero actually. So this is discontinuous, this function. So it's not a linear function as a function of X. Okay. It turns out, but this is very common in these class of problems. It turns out you can actually model this also using the same lot sizing. In the lot sizing problem, you can model this using, so we will see that we can model this as a shortest path problem. Okay. Is this clear? The cost, the way it is written? Okay. So we're going to model this as a shortest path. Okay. Okay. So model as a shortest path. Okay. Now to do this, but we have to modify the graph. Okay. I'll explain this on a modified graph as follows. Okay. So I need to, so why can you, I mean, it's not clear a priori that you can solve this as a shortest path problem. It's not linear costs. So why can you do this? So there's something about this problem structure. Okay. So the key idea is for this problem, and this is where analysis of problem to problem you require to do. So the claim is at an optimal solution, you either produce in period T or carry inventory from T minus 1 to T, but not both. So there's never going to be a time. So the claim is you can look at the optimal solution structure of this problem will be such that you either produce in a time period or you carry forward inventory. You don't do both things simultaneously. If you're doing both things simultaneously, you're not being optimal. Okay. Why is this the case? Is it clear what this is? You do one of two things. You either decide to produce in a period or you carry forward inventory. Both together will not happen in an optimal solution. Or at least it's not going to be optimal to do this. Okay. So why? So once you see this, or once this intuition is clear, we can formulate the shortest path problem. Okay. So I'm just going to show this to you with an example. Okay. To make this clear. So let's say I've got maybe a 5 time period problem. I mean, it might be more than this, but let's say I'm looking at a problem where, let's say at time period 5, and maybe there are more time periods, that's fine. Let's say I've got at time period 5, let's say I'm producing something and I'm carrying forward inventory too. So this plus simply means that there's some flow, there's some production, and there is some inventory being carried forward. Okay. So suppose, so X5 is positive and I4 is positive. Okay. I'll claim that you can modify the solution to get a better cost. Okay. Say, okay, so because there's some inventory coming in, there has to be some production in some earlier time period. Okay. So let's say time period 2 is the last time we produced before period 5. Okay. So that means It could be anything. It could be 2, it could be 3, it could be 4. Let's say time period 2. Okay, I'm just choosing some number. Okay, that means in time period 3, I don't produce anything. In time period 4, I don't produce anything. I might have demands here. I will satisfy that with earlier productions I have done. Okay, so there's some positive flow. This, I didn't produce this, right? So this has to be produced in time period, in some earlier time period. This flow has to come from some earlier time periods. Okay, so let's say this is the last time I produced. So there has to be some positive flow. I mean, there could be some flows here. That doesn't matter for the earlier problems. Okay. Okay. Is the setup clear so far? Okay. Now, what is the cost that this flow is going to incur? There's a cost C5 on this arc. There's a cost C2. There are costs H2. I'm sorry. Yeah. H2, H3, and H4. Okay. Okay. So we're going to look at, so there's basically a cycle in this graph. Okay. There's a cycle, not directed, undirected cycle. 0, 2, 3, 4, 5. This is a cycle. Okay. Can you see the cycle here where there's positive flow? Okay. So let's look at, let's say delta is I'm going to add up all these costs. Okay. For now, forget the fixed cost for time being. So C2 plus H2 plus H3 plus H4 minus C5. All these are pointing in the forward direction in the cycle. This is pointing in the reverse direction. So let's just compute this number, which is the sum of this production plus inventory costs, subtract away this production cost. Okay. So this number delta can either be positive or negative or zero. Okay. So what happens if delta is positive? So if delta is positive, that means this cost, the sum of these costs, is greater than the sum of this cost. Then why would I be sending some positive flow along this and not using this link to make it in the optimal solution? Why? It cannot be optimal. If this sum of all these costs is more than the sum of this cost, it cannot be optimal to send a positive flow along this and not, because I can simply increase the flow on this link. So all we can do is we can increase flow. We can increase basically, we can increase essentially flow in 0, 5 and decrease in the 0, 2, 3, 4, 5, 2, 3, 4, 2, 3, 4, 5 cycle, right? I mean, there are no upper bounds in this problem. Okay, so right now I'm looking at an uncapacitated problem. If this cost is lower than this cost, that's what this says. Delta is positive. Suppose I'm sending 3 units here, and let's say there is some positive flow here. I will keep decreasing this flow and keep increasing the flow, and it has to be better off. I have to be better off till something becomes zero, basically. Okay. Similarly, if delta was negative, this cost, if delta is negative, it means that this cost is lesser than this cost. Then why should I be sending positive flow on this arc? I will decrease this flow and I will increase this flow. I will just produce more in this time period. It cannot be optimal. Okay. So we can decrease flow in 0, 5 and increase in the 0, 2, all the way up to 5. Okay. Both of these modifications will make the objective function only better off. It will decrease the objective function. So this cannot be optimal, this solution. Okay. The last thing which can happen is delta can be 0. But if delta is 0, I'm producing here. So that means it doesn't matter to me, do I use this or this? But remember, I'm also paying fixed costs. Why should I'm paying a fixed cost here of K5. Is it K or F? F5. F5. I'm paying a fixed cost here of F5 and I'm paying a fixed cost here of F2. I'm already paying fixed costs. Then I can as well move. We can transfer it to any one of these two Because why should I pay two production costs? It doesn't matter to me, right? The variable costs don't change. Why should I pay two production costs in the one production cost, fixed cost? Basically, we can transfer um, to one of the two and decrease one fixed cost. Okay. So is it clear, the structure? Okay. So this structure now tells you something. In the optimal solution at any node, either this is positive or this is positive. Both cannot be positive. I mean, it is possible that both can be zero. I mean, okay, if the demands are, I mean, essentially, it cannot be that both are strictly positive. Okay. I mean, if you have some degeneracy, it can be 0 and 0. Okay. But you cannot have both strictly positive. Okay. Okay. Now, what does this mean? This basically means that we can now basically, so this implies at an optimal solution, if you produce in any time period, in any time period, you produce exactly to meet demand for a contiguous, that means continuous, like a consecutive intervals for a contiguous or consecutive number of time periods. Okay. So again, this comes from this structure. What does it mean? If I decide, let's say I'm deciding to produce in time period one, I can decide in time period one to produce only for time period one. I could have decided to produce for time period one and time period two, and I will not say I will produce for a little bit of time period three, and the remaining I'll produce in time period three. This will never happen because we have just said it cannot happen. So if I decide in time period one, I have to decide should I produce for one, one and two, one, two, three, one, two, three, four, and so on. Similarly, for two, I have to decide should I produce for two, two, three, two, three, four, and so on. Okay, which means that you can actually, this implies you can solve it as a shortest path problem in the following way. Okay, so this particular problem, so let's say there are only five time periods for simplicity. I can now actually solve as shortest path on the modified graph. So this is a modification. I'll show you how to do this. So let's say I'm going to have five time periods. Okay. So I'm going to create six nodes. 1, 2, 3, 4, 5, 6. Okay. So if t is equal to 5, I'm going to create six nodes here. Okay. I'm going to have a link from every node I to a later node. Okay. So in this graph, what does the link ij mean? So I've got t plus 1 nodes in this graph, this new graph. The link I comma j, let's say 1 comma 2, it means produce in period I for time periods I plus 1 up to j minus 1. So for example, the link 1, 2 says produce in time period 1 only for time period 1. The link 1, 3 says in time period 1, produce for time periods 1 and 2. Link period 4, 1, 4 says, link 1, 4 says, produce in time period 1 for 1, 2, and 3. So an extreme solution is to produce for all the time periods in time period 1, which is the link 1, 5. Okay. So what I want to do on this graph is I want to find the shortest path from node 1 to node 6. Okay, so what might a shortest path look like? Okay, so I've got to have a cost for this arc. So what is the cost of this arc? So cost of arc ij, you simply calculate. So you add up the fixed cost. So you have to you're producing in time period I, right? So you'll have a fixed cost k fi and the variable production and holding costs. You can calculate this because in time period one, if I produce for time periods one and two, I know what D1 and D2. I mean, I know my costs C1 and C2. I'm sorry. I know my. I'm sorry. My production cost is simply C1. Okay, and my holding cost in time period one. So if I okay, so let's take an example. Take the link 1 3. This link 1 3. What does it mean? I'm going to produce in time period one for time periods one and two. My production cost is C1. My holding cost, I'm carrying forward this inventory from time period, uh, what I produce in time period one, I'm carrying that forward to time period two because I'm satisfying demand for time period two using time period one. So it'll be F plus C1 plus H1. Is that clear? Or do you see what I'm saying here? Or maybe it's you want an example? You want numbers, or I just tell you with so okay, let's take a link. Okay, let's take the link 1 comma 2. Okay, what does a link 1 comma 2 mean? It means I'm producing in time period 1 only for time period 1. What is the cost of this? The fixed production cost, F1. Okay, that's the cost I'm paying, plus my variable cost, which I'm paying for producing this item. Okay, so it'll be plus this, it'll be C1. Actually, it should be C1 times, I should have D1, yeah. So by the way, sorry, this should be F1 plus this amount, this should be plus C1 times D1 plus D2 plus H1 D2. This is the cost I'm paying for in time period one. I'm producing only for time period one. That demand is D1. Every item of production unit cost is C1. So C1 times D1 is the cost of producing for time period for that units, and I pay the fixed cost. Okay. Now let's take 1 3. What happens in 1 3? This cost of this will be F1 plus, sorry, just give me a minute. My phone is continuously ringing. F1. So I produce in time period one. I produce in time period one for time. So this time periods one and two, which means I'm satisfying demands D1 and D2. The production cost is C1 because I'm now producing everything in time period one. What other cost do I pay? I'm carrying the D for time period two. I'm carrying inventory from time period one. So it'll be plus H1 into D2 because these number of units I'm carrying from time period one to two. You can calculate this for every link now. Similarly. Okay. What is a path in this graph? Let's take an example of a path. A path. So let's say my path is I go from 1 to 3. Then let's say go from 3 to 4 maybe. And then I go from 4 to 6. This is a path, right? I can send one unit of flow along this path. So I go 1 3, 1 unit of flow, 3 4, and 4 6. What is this telling me? It's actually a production plan. What is this production plan? This production plan says in time period 1, produce for time periods 1 and 2. In time period 3, produce only for time period 3. In time period 4, produce for time periods 4 and 5, and you're done. That's a production plan. Every path from 1 to 6 gives me a production plan. So in this network, every path from 1 to node t plus 1, or in this case 6, gives me a production plan, and the costs are exactly what you expect, right? The costs are exactly, I mean, if I take this particular plan, this is the cost for producing in time periods 1 for 1 and 2. I will have a cost here which will be F3. I mean, you can write this. It'll be F3 plus C3 D3. That's production in time period 3 for only for time period 3. This will be F4 plus C4 D5 plus D6 plus C5 D5, basically. That will give you the entire cost. So the shortest path on this gives you the optimal solution, basically. Shortest path solves the lot sizing problem. Okay. So this basically requires one to realize that you can take this production planning problem, which is not originally a shortest path problem, but by appropriately creating a new graph, you can create a shortest path problem. Okay, and this is a trick very often played in network optimization. You try to reformulate such, not every problem you can do this. Okay, here's a nice class of problems where you can do this. Okay, and this works on this simple property that in these problems, you have to produce for a content. I mean, it turns out the optimal solution will simply produce for a continuous number of time periods. And then for the remaining time period, you'll plan again then. Should you produce for 1, 2, 3, and so on? Okay. Was that clear, or you want me to spend a bit more time discussing this? I'm not putting numbers here, but hopefully it's clear. Do you want me to do another path, or it's okay? It's okay? It's okay? Okay, good. Okay. So I want to just spend maybe 10 more minutes. I just want to at least introduce the max flow problem. I think we'll not be able to go beyond that. So shortest path we have seen. Let's do max flow. So maximum flow. Again, a very important class of network flow problems. Okay. So what's this problem? So this is going to be different to shortest path. So given a directed graph, again, a very, very important class of network optimization problems. Given a directed graph, again, I'm going to have source node S and sink or end, let's call this sink node T with, now there are no costs on the arcs, but there are capacities with arc upper bound capacities Uij, which is non-negative for every arc in this graph. Find maximum flow you can send from S to T. Okay. So in shortest path, the only thing is there's a graph, there's a source node, a sink node, and there are costs. In this problem, there is a graph, source node, sink node. Now there are no costs, there are capacities, and these are upper bound capacities. What I'm trying to figure out in this problem is if I can send 5 units of flow on this link and 10 units on this link and 7 units on this link, the graph structure forces me to satisfy flow conservation. What is the maximum amount of flow I can send from one part to another part? Okay. The origins of this problem actually is in World War. In World War, they were trying to transport, trucks, battle, army, they're trying to send these tanks from one part of the country to some other part. So what is the maximum amount of flow I can send to get in this network, basically? So that's where it originated from. But now this class of problem shows up, trying to figure out how much can you send on a network, basically. Okay. So how do you formulate this as a max flow problem? So here's the problem. Let me write it down first. So again, we can formulate this actually as a min cost flow, but let me first write it as a maximization problem. So here's the LP. So you're going to have flow conservation at node I. So this is the incoming flow into node I. Outgoing minus incoming should be equal to, now previously my external supplies and demands were fixed. Now I'm making the supply at node S to be a variable, call it V. Okay. So if it's a source node, so if I'm looking at the source node, I've got a flow V, which is my external supply. If it is a sink node, it's minus V to say it's a sink node, and it is zero otherwise. Okay. Where Xij is between 0 and Uij for every edge in this graph. Okay. So there are my flow conservation constraints. There's only one extra variable here, which I'm calling V. This is one formulation of the problem. Okay. Well, this is now a decision variable. Okay. So let's take it again. This is an LP. It's very clear. It turns out this is maximizing the flow in this problem. Let's do an example to illustrate this. Okay. Is the formulation clear? I'm trying to, so maybe I'll show you an example. Okay. Let's take a network, and then we can come back to this formulation if it's unclear. Let's keep the network simple. There is a capacity on every link. I'm going to give you numbers here: 3, 2, 1, 1, 3. Okay. So each of these numbers is a capacity. Okay. What does it say? It says on this link from 2 to 4, I can send up to 1 unit of flow. Between 1 and 2, I can send up to 3 units of flow. Okay. Okay. Let's say my source node is 1 and my sink node is 4. What is max flow telling me? It's saying, suppose I can send V units of flow from 1 up to node 4. What is the maximum amount of V I can send so that each of these flows is no bigger than the capacity of that link and it satisfies flow conservation? Okay. Is it clear? Okay, let's just try to maybe look at the problem and try to figure out what the optimal solution might be. I'm sending V, I want to maximize V. Okay. So of course I can send 0 units of flow. 0, 0, 0, 0, 0. That's the most uninteresting problem here. I'm trying to maximize this. Okay. So I can send 3 units out and 2 units out. That's 5 units out from this node. So I could have tried to send 5. Take 5, partition 3 and 2. But this 3 gets stuck here because I can only send 1 unit along this and 1 along this. So I'm stuck at this point. I can't send 3 here because I can only send 2 out from here. Okay. So it turns out actually in this problem, and we will come back to this later, the optimal solution actually is 4 units. So actually V star here is 4, the max flow in this graph. Okay. Where you send 4 units from here, you send 2 units on this link and 2 units on this link. So these are flows, the optimal flow. Okay. These 2 units, 1 unit comes down here, 1 unit goes here. This 2 plus 1 adds up, 3 units coming in. So I can send 3 units and my capacity lets me do it. 3 comes in, 4 comes out. So 4 is the best you can do on this network. Okay. So some links are at full capacity. Some links are not at full capacity. The flow conservation is causing this. Okay. Is it clear? Okay. Now, this doesn't look exactly like a min cost flow problem because I've got this extra variable V, right? I mean, previously when I told you min cost flow, I said that these are min cost flow problems. You have, so the right hand side is a fixed number, Vi. Now I've introduced something new here called V, and I made V a variable. It turns out actually it's not difficult to convert this to a min cost flow. All you have to do is you take the same network, take the same network, and this is a trick very often you can play in these classes of these types of problems. You keep everything the same, okay? Only thing you do is you add an extra link going from T back to S. Okay. So I'm going to add, so this is a transformation. Add a link add edge T comma S. So from the sink back to the source, I'm going to add an edge, okay, where this cost CTS is -1, okay, all, and the capacity of this link UTS, I'm going to make it infinity, and all the remaining edges Cij, all other Cij. So remember, there are no costs in my problem in MaxFlow. All other Cij, I simply make it equal to 0. Okay. So in MaxFlow, there is no cost. But let me force all the link costs to be 0, except this cost, I'll make it -1. I'm going to send a flow on this graph. Okay. I'm trying to minimize the negative of the flow, minimize the cost, right? Of my, so what does if the cost is -1 here and all these costs are 0, what will it do? It'll try to minimize negative of this flow, which is the same as maximizing the flow. So I want to maximize the flow on this graph, so maximize this flow so that capacity constraints are met, flow conservation is met. That's exactly max flow. So you can just add an arc back and put a cost of -1, and you can rewrite it back basically. Okay, it's a straightforward transformation. Okay, so though it may not look immediately as a max flow, it's a max flow problem. Okay. 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 Any questions? We are almost out of time, so maybe we'll stop here today for today, and then we'll continue on Friday. So what I'll do on Friday is, so I've gone a little bit slower than what I wanted, but it's fine. On Friday, we will basically I will tell you about some more transformations, and then we'll go to the network simplex algorithm. We won't. I want to sort of draw parallels between how you would do simplex for this network for problems, and then I want to talk a little bit more about uh, like the max flow problem and min cut duality. That's an important. So I want to also talk about duality for network problems, specifically for max flow. There's a very nice duality theory which is important to know. Okay. Okay. We'll stop here. I'll see you on Friday.